Hey, how's it? How's it going, electricity students? My name is Mr. Dalday, and I don't know why I'm introducing myself again. Today's kind of a weird day. Yes, we were supposed to have 2 more students, but we do have 2 other students. Oh no, I just hit my ukulele. Can you put this on the table over there? Alright. Alright. We have 2 students over here. We have 1 student online. We're going to talk today, and we're just going to talk. We're going to do hardcore math. We're going to start off with a conversation. Cool? And I want to kind of get a feeling from you guys and see, well, what do you guys think? What is this interesting and all that kind of stuff? And we're going to talk about gravity. We're not going to talk about electricity to begin with. You guys thinking, where's he going with this? Okay. Do you guys know the equation for the force of gravity?
I believe it's Fg or G multiplied by m1 times m2 over r squared.
Okay, so
G being gravity.
you're saying F equals some G times m1, m2 over r squared.
And G being the gravity.
Where did you learn that?
From you, like last
You learned that from me? I don't remember who teaching
Because
this.
me and you went to a little
Oh, that was just kind of a fun thing.
Yeah.
that we did. Oh, okay. Where'd you learn that?
I learned it in basic physics.
In basic physics. Okay, all right. Kalena, have you seen that before?
No.
Okay, all right, here. Well, why don't we discuss what that is? Because, what is that? I don't understand. All right, G is just a number, okay? Just kind of consider that, hang out and just say, I don't know what that number is. It's some number. It's like the number, it's like pi, okay? So don't freak out. It's just a number. It's just a letter that represents a
Isn't it
number.
like 6.67 times 10 to the...
32 or something. I don't remember. I don't even know. I don't even know. To be honest with you, I don't memorize it. So it's just some number. But I know that it's a number. Are we cool?
Yeah.
All right. And what this is saying is that, like, pretend, can you imagine space? Blank out your mind and just have space in it. That's not that hard to do. Okay, now, put a planet in your mind. And put another planet in your mind. So there's these 2 planets just hanging out in space. Okay? We got planet 1, and we got planet 2. Got it? Now, there's going to be a force pulling them together. You guys agree? Now, the amount of force that pulls them together depends on what? Well, it depends on how big the first planet is.
And the second.
And the second planet.
And how close they are.
If the planet were really big, really massive,
Bigger gravity.
then there would be a bigger force pulling them together. Do you agree with me, Kalena?
Yeah.
Okay, good. All right, we're good on that. And same goes for if the second planet. If the second planet were huge, it would be a big force pulling on it. Agree with me? I'm speaking to Kalena because Kalena, you're the only one who doesn't really know this equation. Now, all I'm trying to do is not pull it out of my butt and throw it up on the board and say memorize it. I kind of want to just go through it, like talk about it. All right. Now let's talk about something else too. Does the moon have an effect on the Earth?
Yeah, very
Yes.
small. But it's still there.
Okay. How does it affects the tides? Does the sun have an effect on the Earth? Gravitational. Yeah, it does. Yeah. Which one has a bigger effect?
The sun or the moon?
The sun or the moon?
The sun.
Done.
Well, the moon is closer. So
The moon is way smaller than the sun.
But it is
The
closer.
sun's like 3 million times more massive than the moon,
It's way closer.
but it's way closer. Oh. So that's another thing that this stuff depends on, right? It depends on like how much force these 2 planets feel on each other depend on how far apart or close they are. You guys agree?
Yeah.
If they're really far apart, what would you say the force is? Is it big or small?
Small.
It's small.
Like stars in other galaxies, you don't feel it. It's pop
Right.
but we don't feel it.
Right. Like a giant star could be super huge, but we don't really feel its gravity, its gravitational pull, because it's so far away. Right? So essentially, the further you are, the bigger the rate the range is, or the R, actually this stands for the radius technically. The bigger the radius is away from each other, the smaller your force is going to be. Does that make sense?
Yeah.
Does that make sense to you, Helena?
Yeah.
We call that inversely proportional, right? Because if the radius goes big, the force goes small. And if you bring those planets close to each other, then they're going to start sucking each other in, and they're going to collide because the radius is small, and so therefore they're going to, hit each other. The force will be bigger. You guys agree?
Yeah.
So that's why that
Yeah.
R is on the bottom. Does that make sense?
Divided by R.
In fact, it's not only divided by R squared, apparently R has twice an effect. R is, it doesn't, like if you double the distance that it is away, it doesn't necessarily cut the force in half. If you double the distance, it actually cuts the force in a quarter. And how do we figure this out? Well, we did experiments. And we did experiments, we did theory, and all that kind of stuff, and we look at the units, and the units were the only thing that works. Cool? Are we cool with this? So if I showed you this equation, you wouldn't freak out, would you? No, then you'd be like, okay, I understand that. Okay. The thing that blows my mind is there's this thing called Coulomb's law. Came up with this by this Danish physicist named Coulomb. I think his first name was, I forgot what it was, Charles, I think. Anyway, Charles Coulomb or somebody like that, anyway. And he came up with this law, and it says this. F equals K Q1 Q2 over R squared.
Okay.
What, doesn't that look like something?
Yeah, it looks like the force of gravity.
It looks like the force of gravity. Isn't that cool?
You know what's actually really cool too?
Is it? Okay, what's really cool too?
When you say you take one of them in a system and you put them both together and you make it, you can tell that the static, the electrostatic, is bigger than the force of gravity. That's why Amber can pick up paper while the Earth is still pulling down the gravitational pull.
Yes. Yes. In fact, we were going to calculate that. You calculated that from the book.
Yeah.
Right. So I mean, we're gonna do that together. But what I'm saying here is, doesn't it kind of blow your mind? Or to me, that's what excites me about physics, is that like the world acts so logically. It blows my mind. Apparently, a rule that governs electrons and charges of particles is very similar, not the same, but very similar to the rule that governs the gravitational pull between planets. The difference is, instead of a G, there's a K, and that's called the Coulomb constant. K is what? K is 8.99 times 10 to the 9 Newton meter squared over Coulomb squared.
Yay.
This is scientific notation. Kalena, you told me that you understand scientific notation. I'm not going to worry about that too much. Victor, you're taking college chemistry. You
Yeah, we
understand
just went over
scientific?
it yesterday.
All right, good. Then scientific notation not that bad for you.
Not bad.
What does Q1 stand for? Q1 stands for the charge on first
Particle.
particle.
Isn't like the absolute value, yeah.
Do you guys get it?
Yeah.
Q2 stands for the charge on second particle. Is that crazy? Are we good?
Yeah.
I honestly, I stand here like dumbfounded a lot of times when I really think about it. It's like this is an equation that governs electricity, and yet it governs the forces of gravity. I think the beauty of it is, I don't know, I'm in shock and awe. But then again, you guys probably be like, I knew that. I don't care. All right, that's fine. That's fine. All right, and now here's my other question is, which way does this force go? If we have two positive things,
Away from each other.
then how do they move? They're going to move
Apart.
towards each other, away from each other, up, down, whatever, what?
Just away.
Just away from
Just away from each other. This guy's going to go that way, and he's going to go that way. Agreed? And if it's a positive negative,
Go together.
right, then they're going to come together. We cool with that?
Yep.
Good? Alright.
Good.
So, here's the thing. And I like this conceptual question that they asked. They said, if you had a proton, which is a positive charge, right? And you had an electron, which is that one right there, and they weren't moving. You just had them, and they were hanging out right next to each other. And they were separated by maybe, I don't know, a centimeter, you know? Or, I mean, some really small distance, but I mean, some distance. They were separated by a distance. Got it? Where would they collide? Would they collide right in the middle?
Closer to the
Would they collide closer to the proton or closer to the electron?
proton.
Proton goes in there.
What do you think, Kalana?
The electron.
Okay, what do you think?
Proton.
Proton. I got the boys over here saying proton. I've got the girls saying electron. The answer is it's actually the proton. Because remember last class we were talking about how incredibly massive that proton is in comparison to the electron, right? It was like a difference of 3 zeros, or 4 zeros, I think.
Yeah.
Wasn't it 5? It was like
No,
10,000.
27 to 31, so it's 4.
Okay, 4 zeros. 1,000 difference. So it's almost like you've got a game of tug of war and you guys are pulling at it, and one guy weighs 1,000 times more than the other dude. Why are you pointing at him? He doesn't weigh 1,000. Or maybe he's 1,000 times stronger than you, right?
Yeah.
You're still both going to be pulled together. It's just you'll probably end up more closer to him, you know, than you pulling him to you. Does that make sense? We cool with that? Now, in physics, if you took regular physics from you, we would have talked about inertia, all of that kind of stuff. But I mean, as long as you kind of get a good intuitive feeling for this, because remember, I'm trying to do this so that I'm teaching you on top of, you know, like I'm teaching you as if this were supposed to be a continued class from last year's physics, but it's, you know, but it's not. So anyway, we talked about a conductor. I have no idea why it went this way. Let's go down. I don't want to bore you. Let's keep moving and go into this stuff. So I think that that's pretty crazy. All right. Here's the hard part. And this part is the part that I'm going to really need to work with Kalena and Victor on. And Austin, I could use your help later on. If you have multiple particles, not just on the same line. So far we've said, okay, if I have a particle here and a particle here, and they're both positive, got it?
Yeah.
Which way would the force go?
Away from each other.
Away from each other.
It would go, like let's say that we nailed this guy down. We put a nail in him. Tack, tack, tack. Which way would this particle go?
Right.
It would just go to the right. Agreed?
Yes.
Okay.
But what if what if I had another particle over here that's positive or something like that, and I nailed that guy down? Which way would this guy go? The one on the right. It would go to the right even faster,
Yeah.
or whatever, right? But here's the hard part: is well, this part might not be that bad. What if I put another particle over here? So I've got 3 altogether. Then, which direction would that one that's allowed to move go?
Yes, diagonal of right.
Northeast.
It would go like 45 degrees
Northeast.
northeast. It would go kind of up and to the right. You guys agree?
Yeah.
The hard part is, well, what happens if it's like over here? What if I don't have that guy over here, but I move him to over here? I nail that guy down. Now we're talking about forces adding. We're adding forces, and that's why they call it added by superposition. We're going to add forces, but here's the thing, is in order to add these forces, before I do it, I'm going to have to do this thing called, using trigonometry, called breaking something up into its vectors. Austin is like, snap, I didn't realize we had to do that this year. Colena's like, snap, I have no idea what that is. And Victor's like, I kind of feel like I know what it is, but snap. Because he's snapping. All right. And so that's going to be my headache today. That's going to be my thing that I'm really going to try to work on. And I spent 2 weeks teaching this to Austin. I think it took him like 4 weeks to get it. So don't feel bad if you don't get it today. You know, if I try to explain it to you and you don't get it. But anyway, let's see. Let's move on, and then we'll come back to a problem like that. Sound good? All right. Coulomb's law. Coulomb stated that in terms of a point charge, but if it's also valid for spherical charge of symmetric charge distributions, as long as the distance is measured from the center. So Coulomb's law is this law right here, this equation right here, applies to point charges. Does that make sense? So that what a point charge is like if I charged this ball, okay, then this isn't a point charge. What a point charge is if I were to shrink a ball down to the size of like an atom. You know, I'm talking about one atom. Those are easy to do. When you talk about like three-dimensional things, you know, a point charge is like a one-dimensional thing because it only has just one point. You know, it doesn't have like a 1, 2, and 3 dimensions. It's not a line. It's not a three-dimensional object. It's just got one point, and that's easy for us to talk about, right?
Yeah.
When we're talking about like other things, like you know this ball, and I charge this ball, or I charge this cup, you know. Now you're talking about like irregular shapes, and then for that you're going to need calculus and all that kind of stuff. It's going to be a big nightmare and all that kind of stuff. But to simplify it, if I were to ask you what's the gravitational pull between these two, you would imagine this as a single point in space, and you would imagine this cup as a single point in space. Does that make sense?
Yeah.
So far, all we've been doing is doing single points in space, but then the reason why they had to make a complicated statement like that is because if you were to get into hardcore physics and you were getting into hardcore calculus, you would have to end up like taking the shape of the object into account, which is kind of cool too. But anyway, let's talk about this, and we'll do our best to go through this. Kalena, I don't mean to make you feel like you're the weakest link here because you're not, but I want you to make sure that you stop me and tell me whether or not you are catching this. You too, Victor.
Okay.
Just because you're brand new to this, all right? I've been working with Austin for like 20 weeks now. So he hasn't learned this stuff, but he should be able to catch on pretty quickly. I haven't worked with you in this level of physics and math and whatnot, and so it gets some getting used to. It takes some getting used to, right? Would you agree?
Oh, yeah.
Like my Mr. Dalday's math will break your head for a while, and then you'll be like, oh, I finally get it. All right. So I know that you can't really read that. I'm going to read it to you. In an effort to understand the behavior of an atom, this Danish physicist Niels Bohr introduced a simple model of a hydrogen, and he said that inside of hydrogen it moves around in a circular orbit. There's an atom that has a circular orbit over there, and I realized this problem is too hard for you to solve. I'm sorry. I realized that the reason why it's too hard for you to solve is because I haven't covered with you circular motion, and I almost feel like it would be wrong of me to cover circular motion right now when I'm covering a new topic, especially breaking components up into their vectors and all that kind of stuff. So let's skip this one right now. Is that cool? Austin could probably do it because I did teach him circular motion, but I didn't teach everybody else. And circular motion was actually kind of hard. All right. But anyway, let's try number 2. Find the electric force between two 1 Coulomb charged particles separated by 1 meter. Okay, so draw the picture. I've got a charged particle and I got a charged particle. I'm going to separate them by 1 meter. The charge on this guy is equal to 1 Coulomb. And I don't want to... You see why I don't use the letter C for charge? Because it says C equals 1C. No, it's Q1 equals 1 Coulomb, and Q2 equals 1 Coulomb. Are we cool?
Yep.
All right.
Right.
Now, the force, how is the force going to act? Are they going to repel each other
Or are they
or attract each other?
positive or negative charges?
Well, it says on two 1 coulomb charges. They don't tell me. They just tell me 1 coulomb.
Well, I guess they'd both be electrons then, because if just talking about coulomb, we go 1.60 times 10 to the negative.
No. You would just say they're 1 coulomb charges.
They're not asking for direction, right? They're just asking for how much charge it has.
They aren't asking for direction, but whenever we do talk about a force, we need to talk about a
You won't
direction
know.
as well. What I'm asking is, all right, whether or not they're positive coulomb, they're positive or negative. Actually, they tell you it's 1 coulomb. So I mean, I'm assuming positive, but you know that they're both the same. At least that's one thing you definitely know.
Yeah.
The value is 1 coulomb, and they're the same. So which way would the force be going?
Away.
Out. Good. All right. Now, all I got to do is plug this into the equation. Force is equal to K Q1 Q2 over R squared. All right. K was 8.99
Times 10 to the 9th.
times 10 to the 9th. What was the units?
Newtons.
Newtons.
Meters squared.
Meters squared divided by coulombs squared. All right. What is the charge on Q1? Well, that's 1 coulomb. Right?
Yep.
What's the charge on Q2? All I'm doing is I'm plugging this straight into there. We good with that, Kalena?
Yeah.
All right. What is the charge on Q2? It's also 1 coulomb. What is the charge on, or what is the distance? It's 1,
Squared.
but it's squared, so it's actually
Just
1 meters squared. Are we cool with that?
Yeah.
All right.
Okay.
Now, look at the units. This meter squared cancels out with that meter squared. Can you hang with that?
And those 2 coulombs cancel each other.
Yeah, we're going to get there. And the coulombs, the units for that, this coulomb squared on the bottom, there's 2 of them on the bottom. I'm going to cancel out both of them on top. We cool?
Or newtons.
So your answer is in newtons, which is good, right? Because
You want
You want
a force is measured in newtons, so that's good. We're on the right track. The answer is, well, I just got to multiply this by 1 and by 1 again and then divide by 1. Are you kidding me? That's just 8.99 times 10 to the 9th newtons. That's my force, which is actually a big force.
A lot of force.
That's a huge force, times 10 to the 9th. We're talking, I think 10 to the 9th is
Isn't it like a
billions?
Yeah.
Yeah, it's billions. You're talking about 8 billion newtons? Do you feel like that's a lot?
That's when we're going over like kinematics before.
Yeah, no, that's huge, humongous.
Yeah.
But then again, we're talking, and this is kind of my thing, is we're talking about 1 coulomb charges. That's a big, big charge. Apparently when this guy Coulomb made up the charge, he ended up making a really big unit. So it's almost like
Was there like any why he did it? Of
um,
course, there was a reason, but like why?
I don't actually know. To be honest with you, I don't know. I don't know the history of that. But it's almost like, here's what I mean is, it's almost like measuring how fast your hair grows or how long your hair is in kilometers. That doesn't really make sense,
Yeah.
right?
Yeah.
1 coulomb is a big, big number. You know what I mean? So what they did was they usually measure things in microcoulombs,
Isn't that
which is times 10 to the negative 6 coulombs.
Yeah.
Because what they're doing is they're cutting down the units so that it's in normal things. Like if I'm going to measure my hair, I'm not going to use kilometers, I'm going to use centimeters maybe.
so it's the same thing for using the microphone.
That's why they're using coulombs versus microcoulombs. We cool?
Yeah.
Yeah.
Alright.
Is microcoulombs negative mu c?
What is that?
Is microcoulombs negative mu c?
Yes, microcoulombs looks like this, by the way.
Say it. Say it.
1 mu c.
I enjoy that Greek letter.
A mu is a U with a tail in front of it. That's the way I look at it.
The Greeks just
It's just a Greek. And it's not that Greeks are messed up, we just don't.
we are just messed up.
Well, it's not that either. But
Well, we can't
It's a Greek letter.
system, so
It's hard to write at you like that.
alright, let's try this one. Ready? A charge Q1 is negative 5.4 microcoulombs. Got it. and is at the origin. All right, so let's draw a graph, and at the origin, which means at 0, 0, let's put a charge there, and that would be Q1 at negative 5.4 times 10 to the negative 6 coulombs. Instead of writing microcoulombs, I'm already going to put times 10 to the negative 6. It's the same thing. We cool? Excuse me.
Bless you.
I've been talking since 9:30. I'm sick and I gotta go sing for 2 hours and then I gotta go teach another
That
class.
sounds fun.
Today is a tough day for me. Alright. Now we got Q2 and it's on the axis and it's 1 meter away. Alright, fine. 1 meter away. We have Q2. Draw this, by the way, Kalena. Equals negative 2.2 times 10 to the negative 6 coulombs. I'm not writing microcoulombs because that's what the times 10 to the negative 6 is going to do. Alright, so it looks to me like these guys are going to repel each other. Find the force acting on a charge that is Q3, that is at 75 or 0.75 meters. And it's Q3 equals positive 1.6 times 10 to the negative 6 coulombs. All right, the way I kind of think of it is like this. You got a girl standing right here. Girls are positive. Boys are negative. You got a boy over here and a boy over here. Got it? And this boy is attracted to that girl. And that boy over there is attracted to that girl. Right? And I guess this boy on the left, would you say he's more attractive than the boy on the right?
Yes.
Oh,
Not really.
No, actually, yeah, they both look like stick figures to me. Well, what I'm saying is like look at the negative. He's negative 5.4.
Yeah.
This guy's only negative 2.2.
And then
yeah,
this.
so
He's gonna be the guy on the left is gonna be more attractive. So who is that, Kalena? Who's the more attractive boy that we're talking? Are we talking Justin Bieber?
Ugh.
I'm just wondering. This
Sounds
Kalena's choice, Kalena.
Stuff.
Who are we talking about?
No.
Oh, is it Channing Tatum?
Okay, he's pretty cool.
That's exactly what I was going to say.
What is that?
Channing Tatum.
All right, we got CT over here, and then who's the kind of attractive boy but less?
I guess he, what's his name? James Franco.
James Franco, JF. There we go.
What do you Dave?
All right, hey, I know, whatever. Okay. That's cool. He's the Pineapple Express guy. And then we have Kalena Exner in the middle. And they're both attracted to you, by the way. The problem is James Franco, who's slightly less attractive than Channing Tatum, is closer to you. So the question that I'm going to ask you is, which way are you going to go? Obviously, you would try to be going towards Channing Tatum, but the fact is she's so far away, they're just like, it's not even worth the effort. This guy is kind of less attractive, but he's closer. So the question is, which one wins? That's really what my question is.
The closer one.
Well, no, I don't know. I don't know.
We gotta figure it out.
Why don't we
do
calculate it
math to
out?
figure out your future.
Why don't we calculate it out? Sound
Use
good?
math to figure out your future.
All right. So what I'm going to do is I'm going to do F31. And that means, what is the force on 3 that's being acted on, or that's being given by 1? Does that make sense? If I have particle number 3, which is in the middle, this is the force that 3 is being pulled on by 1. That's why I have it labeled like that.
Okay.
All right. So that's equal to K Q1 Q3 over R squared, which is what?
Which is 0.75.
0.75 meters squared. Cool?
Okay.
You guys cool?
Okay.
What is, and then we can figure that out. What is F32? That is, what is the force that is James Franco is pulling on you? Well, that's K Q 2 Q3 over what? And by the way, this is,
would be what?
what is it?
0.25.
Y 0.25.
Because 75 and right when CT and KE, so if you just have to pick the one.
Do you understand why it's 0.25, Kalena?
Okay.
Because James Franco is standing 1 meter and you're at 3/4 of a meter. So the distance between you and him is actually only a 1/4 meter. We cool?
Okay.
And then my question, and then what we should do is we should figure out, well, okay, he's pulling in Channing Tatum is pulling in the which direction? Positive or negative?
The negative.
Is he pulling to the right or the left?
Oh,
He's pulling to the
right.
negative direction.
What?
So, and then James Franco is pulling to the right. And so what we'll do is, why don't we add these two together?
It makes confusing.
And if the number is positive, if the overall force is positive, that means you're going towards James Franco. I'm sorry. I know that Channing Tatum's prettier, but he's just close. He's farther away. And if the number ends up being negative, that means you're actually going towards Channing Tatum, because James Franco is, just not that good looking.
Oh yeah, I am getting the names. Okay, I was like, right.
Yeah.
Does that make sense?
The names wrong.
Are we cool with that?
Yeah.
All right. Okay. So let's calculate this out. What is F31 plus F32, which is
Negative 0.1.
negative. Great. 8.99 times 10 to the negative 9
So is it right up?
times Q1, which is negative 5.4 times 10 to the negative 6. I'm not going to put units because I actually know that the units will work out. I'm going to assume that you guys know that too. Q3 was 1.6 times 10 to the negative 6. And by the way, I don't need this negative out in front. Would you guys like to know why?
Which negative?
See this negative out in front?
Yeah.
This negative right here, I don't actually need that.
I don't see the negative.
You don't see it because I turned it into a positive.
Why? Is it because there's just two negatives and it just cancels out?
Because look, the math already accounted for it. There's a negative here and there's a positive here. When I multiply those two together,
Okay, and
it's going to end up being negative. And the math told me that it already knows what it's going to do.
Alright.
All right, and you divide that by 0.75 squared.
So you already know it's going to be negative.
Do you know how to do this, by the way, on your calculator? I'm just curious. I know you know how to do it. Do you know how to do it? Because it's scientific notation. Do you know how?
Yeah.
All right, I'll show you. Here's what I want you to do on your calculator. Multiply 8.99
Okay.
times 5.4.
Times 5.4.
Yeah, just times 5.4
Okay.
times 1.6.
Ah, we're doing it this way.
What is it?
I got 77.6736.
77.636.
6736.
6736. Right? And all I did was I just multiplied the numbers part, but I didn't multiply the exponent part.
Ah.
You guys got that?
Yeah.
All right.
Yeah.
Now, I know that the answer is going to be negative because I have a positive times a negative times a positive. Are we cool?
Yeah.
Now let's deal with the exponents. What is 10 to the negative 9 times 10 to the negative 6 times 10 to the negative 6?
10 to the negative 21.
10 to the negative 21. Do you understand how to do that part, the exponent part? Kalena or Austin? Austin's kind of looking like, I'm curious, what is he doing? And I almost feel like I'm not going to get into superposition today. I'm just going to teach you guys how to do scientific notation and that kind of stuff. And remember, I'm covering the hardcore topic at toddler pace. So I don't mind if we don't get that far. I'm going to adjust your homework. We're going to do that, and I'm going to tell you guys about a cool project I have.
For the constant K, I'm wondering about the negative 9.
Huh?
I just was wondering. The
Oh,
negative 9?
no, you're absolutely right. It's not a negative 9. It's supposed to be a positive 9. That's a constant K, right?
Yeah.
I'm sorry. I made that
So
mistake. So
changed.
that wouldn't change the numbers, but what it would do is change the exponent. How would that change? Do you know? it would make it times 10 to the negative 3.
Oh.
How did he get that? What happened?
We left out. We forgot it was a positive value.
You don't know?
It was a positive value.
No.
Okay. What I did was I was multiplying the numbers 10 to the positive 9 times 10 to the negative 6 times 10 to the negative 6. Got it? I'm going to show you guys how to multiply numbers that have the same base but different exponents. You want to know what you do?
You add them.
You straight up add the exponents, and that's it. You keep the same base, you add the exponents.
Oh.
9 minus 6 minus 6 is actually
minus
negative 3.
Yay.
Now,
Okay.
that's something that Mr. Dalday, remember, Mr. Dalday said, I don't like you pulling equations out of my butt, throwing it up on the board and saying, memorize it. I don't like telling you that rule without telling you why. Fine, I'll tell you why. 10 to the 9th power is actually 10 times 10, 10, 10, 10, 10, 10. All right, 1, 2, 3, 4, 5, 6, 7, 8, 9. And there's a multiplication in between all of these. Got it?
Yay.
10 to the negative 6 is actually in the denominator.
So you just can start canceling out
Yeah.
tens? Oh.
All right, so that's 1, 2, 3, 4, 5, 6. Good. And then we have another 10 to the negative 6.
4, 5,
Are we cool?
6. Yay.
All right, so now we're going to cancel out a 10. Any 10 we cancel out on top, we're going to cancel out on bottom. Here, 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 here. There we go. Uh-huh. Yep. And that one.
Yay.
Guess what? There's 3 10s left in the denominator. That's why it's times 10 to the negative 3.
So if it's in the numerator, it would be a positive. You said-
If it's in the numerator, it would be a positive number.
Basically
Isn't it?
flipping 1 over 10 over 3. And
Are we cool with that, Kalena? Do you like my explanation?
Yeah.
But you see, that's the thing. That's
Makes it
the
much
beauty
easier.
of it. Is the beauty of doing scientific notation is you're doing crazy, crazy, crazy multiplication
So we
using addition and subtraction.
Yeah.
I made times 10 to the, or 10 to the negative or 10 to the positive 9 times 10 to the negative 6 times 10 to the negative 6
10 billion.
into what is 9 minus 6 minus 6? Negative 3.
So 10
I made it into addition subtraction. Isn't that cool? Anyway, I don't know if you think it's cool. Anyway, whatever. Let's keep moving on. All right. So what you do is you divide this by 0.75 squared, and then you plug that into your calculator, and your answer ends up coming out to be negative 0.14 newtons.
So what's the reason why we're using the 0.75?
0.75 because that is the distance that Channing Tatum is away
Okay,
from
so
us.
that's what so we're trying to do 3.
Yeah, this is just the first part. I didn't do F32 yet. I just did F31.
Okay.
Oh, really? That's actually so much.
Let's do F32.
So much cleaner.
F32 is 8.99 times 10 to the positive 9 times negative, what is it, 2.2 something, right? Yeah, 2.2. Or no, not, yeah, it's negative 2.2.
Screen went black.
Negative 2.2 times 10 to the negative 6 times, what was Kalena? 1.6?
And that's 77.6136.
That's 2.2.
No, I'm looking at the back. I'm just trying to write everything down.
Oh, it's 7.6.
Okay.
Yeah. And then this would be divided by 0.25 squared. And you know what? I think I realized I told you something wrong. Remember, it's been a while since I did this. I told you something wrong, I'm pretty sure. That negative does not actually cancel out.
Oh, it doesn't, because you have to
Because
go
there's a
in the
negative
direction
over
of
here, and actually that one's supposed to be pulling you
the
forward.
charge. You need the direction of the charge.
Right. So, you know, we have to take that into account at the end. Anyway, when we multiply this together, we end up getting All right, do this for me. 8.99 times 2.2 times 1.6, and what is that going to equal?
8.99 times what?
2.2
times
times 1.6,
okay.
and that equals to
31.644.
31.644
8.
times 10 to the negative 3 divided by 0.25 squared.
So are we only using like 3 decimal places?
Yeah, well, it doesn't even. I mean, yeah, sure. And then you calculate that out, and you end up getting 0.51 newtons.
645 then.
All right, 645. Fine. Okay, fine. All right. So look, check this out, Kalena. Channing Tatum
Yeah.
is pulling backwards on you at 0.14 newtons, but James Franco is pulling forward on you at 50.51 newtons. I'm sorry to say this, but it looks to me that if you're standing out at 0.75, James Franco's going to win.
Okay.
And then Kalena's like, well, darn, I guess I'll have to end up with James Franco. And he'll be all upset about it. And I'll just be like, well, not that bad. Right?
Yeah, something.
Yeah. And by the way, when I mean end up, I mean like you get to hang out and have a chocolate sundae, because I know that your brother's over here just like, nobody's going to hang out with my sister. So, I mean, that's what I was saying. You know, I mean, who gets to eat chocolate sundaes with Kalena Exner? And they're all like, ooh, I want to eat chocolate sundaes with Kalena Exner. Right. That's totally Channing Tatum. Oh, come on. You would totally be like, ooh, I want to eat chocolate sundaes with Channing Tatum.
Because he's Duke in G.I. Joe.
He is Duke, but then he died.
I know, that's...
Anyway. Alright. I'll tell you what. 3 charges. Okay, I'll tell you what.
Do the vector addition thing.
I am not going to cover superposition today. I think that this stuff is hard enough as is. I think this stuff is challenging enough as is for Kalena and Deja and Asia, and maybe not you guys, but I mean, I think that you guys did this, and you guys were like, oh, can you check my work, because I don't even know if I've got it correct.
I was more confused with the
Alright.
the one where you have 4 points and I don't know which way.
Right. Let me show that to you on Wednesday.
Okay.
I'm taking this slow, okay?
On the pace.
And to be honest with you, I feel like this is a good amount of stuff to know today,
For the week.
right? This would be, I mean, hitting that scientific notation and plugging it into this equation, working with these units, which is funky. You know, understanding that microcoulombs is actually 10 to the negative 6. By the way, I need to show you my project. I want to do a project that I think is pretty cool. I was thinking about doing a project that mixes up the PA class, because a lot of my students are in PA, so you guys are like guitar musicians or whatever. And so I brought in a guitar, and I was thinking, you know what we could do is I can teach the PA class about acoustic dynamics and talking about like how to build guitars, because I build guitars and ukuleles and all that kind of stuff. In fact, that ukulele that's right there I built, and then I built, I didn't build this one, but this is a guitar that I'm working on. It's a Gibson SG, but it's hollowed out. I got no electronics inside.
Did you just buy the body, or did you make the body? Just with the boys?
I found the body. Actually, I got the body from my cousin. The head was broken off. You can obviously see that
Oh,
there.
yeah, that happened to my guitar too.
Yeah, somebody went like, yeah!
Oh no, it was just we just left it in the car.
Alright, so the head broke off.
I don't know.
So I actually I glued the head there, and then the
Once you finish it, that'd be pretty good.
the bottom was cut, broken off too. Somebody went crazy with this guitar. So then they gave it to me for free, and then I know how to do woodworking really well, so I put it all back together.
Ooh.
It's pretty, right?
Pretty.
So maybe as an electronics class, we'll put the electronics in this thing, and then as a music class, I'll teach you guys about like building instruments and woodworking.
Or distortion pedal.
And then also in electronics class, I think it'd be cool to build a distortion pedal.
Yay.
So like I need to teach you guys about this stuff before I teach you about distortion pedals and circuits and all that kind of stuff. This is my motivation. You guys think that that's going to be a cool project for electricity class?
Yeah.
All right, cool.
That sounds fun.
All right.
Actually learned something.
So I want you guys to come in. We'll actually build an electric guitar and then build a distortion pedal, and maybe we'll build our own. Because actually, when I was in electronics class, my teacher let me do like, Tosh, do a project, something you think might be fun. And I said, okay, you know what would be really fun is if I made a radar gun.
Ooh.
Is this the story where your friend made the REMS laser sleeve?
Yeah, I have a friend who made this friend in this
What,
same
on
class did a REM radar sleeve, but I made a radar gun. And I went out and did the research, I bought all of the components, I designed the circuit myself, and then I built a radar gun.
Didn't you make it on microwaves or something?
I made it, out of microwaves. And
Dangerous.
it's, no, it's not dangerous. You basically shoot this wave, it bounces off something, and then it comes back, and based off the Doppler shift, you can figure out how fast the thing was going. It turns out that my friend's project, who I worked on a lot of his stuff with him, ended up being something that he made a career out of, and then he ended up now is like selling it to NASA, and they have it on the space station, and I'm totally 100% jealous because, I mean, he worked for NASA, and I'm not to say that like I'm disappointed being a science teacher.
Working at MBTA.
I like working at MBTA.
You just wish you were at NASA.
I mean, I wouldn't mind being at NASA, but I'm just saying. Yeah, I get to build SG guitars. I'm sure that he gets to buy SG guitars, like,
Just
keep going. So, anyway, this is my project that I have working on. Kalena, I have a question, because I feel like these guys feel like they might be a little bit cheated with, like, hey, we're not going as fast as I want. Is this digestible to you?
Yeah, it's starting to make sense.
Good. Let's keep that pace then.
Yeah.
So I'm actually going slower than even I thought I would.
Wow.
But that's fine. I'm going to go at your pace. Because I'm going to teach you cool stuff at your pace. Because the alternative is I'll teach you the baby stuff, which isn't as cool at all, and teach it too fast. As a student, I don't care about doing baby stuff. I want to do cool stuff.
Yeah.
I want to do the big kid stuff. Right? That's my goal. Cool? This is big kid stuff. Anyway. Gibson SG is the king of the guitars.
Semi-air guitar.
Yeah. Alright, so I'm going to end the archive there. I'm going to adjust your homework so that way it's reasonable when you compare it to what we finished in lecture. And have at it. So your homework that's due today is actually probably going to be pushed back like a week. But I'll probably make one or two of the problems that I gave from there due soon. Because that's what we covered in class. Sound good?
Yeah.
Sound fair?
Yeah.
All right.
So you spelled dropouts with an E.